So let's suppose we want to talk about the roots of this polynomial. And we've got these complex coefficients. Now, when I say complex coefficients, remember, real numbers are also complex numbers. So when I say complex coefficients, I'm not talking about numbers that necessarily have an I component. So the number 2, for example, is a complex number. But you think of it as having the imaginary part being 0, so it would be like 2 plus 0i. So what I'm going to use in this video is numbers that have a 0 imaginary part. I'll just call those real numbers. And numbers that have an imaginary part, I'll refer to those as non-real. Now, I don't know if that's the best way to do this, but some people would call numbers with a 0 imaginary part, they would call those purely real numbers. And then the numbers that have the imaginary part, they would call those complex numbers. But I'm not going to do that here. I'm going to use real numbers and non-real. Okay, so what I'm going to do is talk about the fundamental theorem of algebra and just give you kind of an overview of what it states. Let's suppose I have this graph. And this is the graph of a polynomial. And I'm going to say that it's, in particular, the graph of this 5th degree polynomial. And notice it has 5 real roots. See? 1, 2, 3, 4, 5. 5 real roots. Now, what I could do with this polynomial is I could increase this f, this number on the end. If I increase it and raise this graph up a bit, notice what happens to these 2 roots right here. These 2 roots are together. Watch what happens if I raise it up a bit. This graph no longer crosses the axis at -2 and -1 because the graph has been shifted up, and now notice it's elevated above. So what happens here is, now notice the real roots. We still have 3 real roots. 1, 2, 3. But these 2 roots, these roots right here that were the real roots, we've kind of traded those in for 2 non-real roots. In other words, we've traded those real roots in for roots with a non-zero imaginary part. So we have 3 real roots and 2 non-real roots. But nevertheless, notice we have 5 complex roots, right? 3 and 2 there and 5 here. 5 real ones here. Now take note of this. Look over here at this one. Look at these 2 real roots here, and I will increase f by a little more. And now look what happens. Now we only have 1 real root. And now we have 4 non-real roots. Now notice this. An observation that you want to make here is that these non-real roots travel in pairs. You're never going to have a situation where you have 1 non-real root or 3 non-real roots. You're either going to have 2, 4, 6, 8. Of course, you could have 0, but they travel in conjugate pairs. So for example, if 1 plus 2i is a complex root, a non-real complex root, then 2 minus 3i is also. Okay, so let's look at an example. Let's suppose we have a polynomial and it has these 3 roots. 3, 1 minus 2i, 1 plus 2i. And we want to write the formula for that. Well, here we go. Now, we don't care what the y-intercept is or anything else. We just want a polynomial with these 3 roots. So notice, we have x minus 1 minus 2i, and then x minus its conjugate, 1 plus 2i. See that? This is always what we do. If we're given the roots, we can find the factors by just doing x minus whatever that root is. And then, of course, on the end here, we have x minus 3. Now, I want to go through here, and I've got some algebra to perform here because I want to expand this out, and when we're done, we're not going to have any i's in there. It's just going to be x's. Now, here's the trick I like to use when I'm going to multiply something like this out. I like to take this x minus 1 and group it like I've done here. And then when I distribute the minus here, notice it's a plus 2i. So you see that? X minus 1 plus 2i. That's this factor right here. Now I'm going to do the same thing for this one. X minus 1, see that? X minus 1 right there, minus 2i. See, I distribute the minus through. And then, of course, the x minus 3 over here on the end. Now, the reason I did that is because it's going to make the multiplication a little bit easier. Because look at this. I've got x minus 1 plus 2i, x minus 1 minus 2i. Well, that's like a minus b times a plus b, which is a squared minus b squared. So in other words, this multiplying, I don't really have to do a lot of work because I know what that's going to look like. It's going to be the first term squared minus the second term squared. We've done that so much, we don't have to reinvent the wheel every time. And then we've got the x minus 3 over here. Now, now remember this I squared I can replace with negative 1. So now we have x minus 1 squared plus 4. See? This minus 4i squared becomes plus 4 right there. And I went ahead and expanded this. See? I expanded that binomial right here, and then the plus 4 right here. Then I just multiply this out. And there we have it. Okay, so I'm getting ready. I went ahead and added those. I didn't multiply it yet. Okay, so there we go. Now I multiplied it. And this is the polynomial with these 3 roots. And notice it's a third degree polynomial. And the graph of it, it looks something like this. We have a y-intercept down here, and here's that one real root right there. But here's the thing, what the fundamental theorem of calculus tells us that if we have a polynomial with complex coefficients, an nth degree polynomial, there's going to be n complex roots. And that includes multiplicity. So for example, f of x equals x squared. It has 2 complex roots, 0 with multiplicity 2. So even though you might say, well, that only has 1 root, 0. No, we count the multiplicity. And that's what this fundamental theorem of algebra tells us.